So in the previous part of our videos, we actually talked about the pre-warping in lecture 8. Alright, then in the lecture 9 or the previous videos along, we talk about the mesh pole 0 method. Alright, and these design techniques in the introduction we have say that is called emulation also, because you are changing your digital signal by a bit. Alright, in order to alter your digital signal such that it is better. Alright. Now we're going to have another method to control or to design your controller. Alright, just now we are talking, what we have been talking on for many videos is talking about emulation techniques or design in terms of emulation. Now we're going to design in terms of a discrete system, alright, where we have a 0th order whole. Alright, so I don't know what are all this. This is difference equation and Z transform. So I think these are all 0th order whole, I think. But any of this case, this is what we're gonna do now. Alright, if you didn't watch 0th order whole, I'll just recommend you to watch l9v8, v2, v3, v4, v5, v6. Alright, these 6 videos in the playlist will actually help you to fully understand 0th order whole. Alright, so before I continue, you watch that first. If you came from the previous videos or you came from that particular videos, let's carry on. Alright, so we understand that normally if you take 0th order whole, this is your analog signal, and then you take the samples over at this side. So at first this is, maybe my pen is too thick. Yeah. This is the analog signal. Over at the sampler, you're taking samples of the analog signals, and after that you hold it, alright, as we have said, and then you change it back to a Laplace domain with some transfer function, okay, and after that you switch it to the time domain, and after the time domain over here you're gonna sample again. Alright, because at the time domain over here you need to sample. This is the sampling of the output so that the digital will actually output to the system. Alright, so this form is actually a bit ineffective because, for example, you take the input, you sample, and then you hold. Over at this side is a digital already, or maybe I should say that over at this side is a digital. Okay, and then you convert to analog, and then you sampling back into a digital. You see, that's a bit inefficient, right? Over at this side. So I repeat again. Over here, I think you still quite understand what I mean, because this is the analog. You sample it, and then you hold it. It becomes a digital. But over here, there is totally no point in doing so, because you want to convert back to the time domain and retake the sampling data in order to output to a digital system. Alright, so in other words, this thing over here, why is my box? This thing over here, or maybe I should say that this thing over here is equals to this portion over here. Okay, or this thing is simply your Laplace domain, because in order to convert digital back to the time domain, you need to Laplace first and then convert to the time domain. And the time domain, because they want to output, so they take in the time domain analog signal and sample back again to the digital, so they'll output into a digital monitor or whatever. So therefore, as you can hear or listen and understand, this is totally very inefficient. Alright, and therefore in practice they normally don't use this method, because they just want to convey to you that this is supposedly how it's being calculated and things like that. But for our case, alright, since we already understand how this thing comes from, this is your delay, your 0th order whole, this thing over here is your 0th order whole. If you don't understand where this is come from, just watch this video. I think l9v8, they'll talk about that if you forgot lah. Alright, so therefore we want to actually cut short this method. Alright, while we do want to convert into the time domain, because since our output is in terms of a digital, we can actually cut short by actually bring this all the way to here. Bam, right? You can straight away bring it to here and then you output to a digital system, and that's it. Finish. Happy. Correct? So therefore what we can do is actually to use this equation, 0th order whole. Alright, while your transfer function straight away divide by s. Okay, and how do we do this? Alright, and nonetheless we are still talking about designing a controller. Okay, now in terms of the zeroth order whole, not by emulation. Alright, and just a recap is that emulation can be alliancing because you times 2 your whatever frequency. Alright, you can also use the pre-warp tasking method, or you can use the zeroth pole method, which mesh method, which is we have just discussed. Alright, so these are the things that you may need to fully understand, and therefore let's just continue with the zeroth order whole. So if you were to ask to actually settle off this equation, a over s plus a, for example, which is your low pass frequency, if you want to zeroth order whole this thing and then output to a certain whatever stuff, alright, so you actually convert to a digital already. Now you want to go into a certain transfer function, alright, after going through a certain transfer function machine, and then you want to actually output to a digital one. So if you want to output to a digital one, actually you no need to go through changing back to the time domain. You can straight away change it to the k domain, alright, or the digital domain. So therefore this is the shortcut method to do, and it's actually pretty easy. So for example, if your transfer function is h of s, so you just sub in over here lah. So what we have is 1 minus z minus 1, leave it here first, and then you z transform your a over s plus a divided by s. Okay, so in other words, this portion over here can be rewritten as like this. Okay, because you just divide by s. Your h of s is this one. If you were to divide by s, you have this thing over here. Okay, I don't think I need to prove to you. I just need to prove to you lah. Okay, so if a over s plus a, or your transfer function divided by s, then by the very primitive method is to change it to times 1 over s, right? Because divide by s, if you were to change it to multiply, it will become 1 over s, right? This is the very old method of solving any algebra question. So I'll just take it as times 1 over s, so therefore I have a s plus a, okay, which is this one. Alright, in case that you may have difficulty in trying to do that. But anyway, let's continue. So therefore what I can do now is to actually to solve for this, right? Because now it's in terms of something that is not good for us. Because you cannot simply z transform this convolution, because it's 1 over s convolution with a over s plus a. Alright, if you look into the Laplace z transform table, you can't actually find them. Alright, you need to actually break it down first. Alright, so I would have 1 over s, alright, maybe I should write it as a partial fraction, a over s plus b over s plus a. Alright, and over here it requires a cover up rule. The cover up rule is if you were to cover up the s, if s is equals to 0, alright, then, okay, so the cover up rule says that this, alright, so if my s is equals to 0, I'll just cover up this particular portion, alright, actually not lah, I'll cover up this particular portion because this portion over here belongs to this, right, a over s, or this portion over here, s plus a, is equals to belongs to here. If you don't understand anything, you just watch this video coming from this one. You just type in partial cover up rule, YouTube, normally you will just come out this one. This is the first video you can find. Alright, but anyway, which is over here now, right, what we can do is, if my s is equals to 0, or my s is equals to 0 over here, alright, then what can I have? If s is equals to 0, I'll cover up this part. This part is gone. So if my s is equals to 0, 0 plus a is equals to 1. Alright, so therefore, which is equals to a. Okay, so I repeat again. If I want to find the roots of this portion over here, I just sub in s is equals to 0. Alright, so if I sub in here, this thing will be covered up, then this one becomes 0, so a over a is equals to 1, which is equals to this a. Alright, this portion over here, ignore first. Okay, hope this is pretty clear. Alright, we need some numbers, that's why if you were to just watch this video, these numbers will be more apparent to you, and you get to know it quite well. If you understand what I mean, then I can just continue lah. Alright, so over here, my roots over here is minus a, correct? So if I were to sub in minus a, I carve out this portion over here, I'll have minus a. Alright, so this thing s is equals to minus a lah. Alright, so therefore I have a over minus a, which is equals to minus 1. Alright, so it's equals to my b. Okay, because this roots of this particular stuff, alright, is equals to this thing. Alright, hope you get what I mean. Yeah, that's why you just go and watch the video. So we know that a is equals to 1, b is equals to negative 1, so therefore 1 over s plus b is minus 1, right? So I should just write here first, then minus 1 s plus a. So I can rewrite as 1 over s minus 1 over s plus a. Okay, which is in your book lah. The same thing as your book. So this is just a partial fraction form of method solving. Alright, so I'll just write it here. Alright, I just need to write this as 1 over s minus 1 over s plus a. Okay, nonetheless, you can also memorize, this form can be partial fraction into this form. Okay, but the key method, if you just to recap to you, is that 0th order whole, your transfer function need to divide by s. Okay, please take note of that. Alright, while the 0th order whole standard equation still stays here. Okay, I didn't move that. Now 1 over s and 1 over s plus a, we can just simply go and find your Laplace table, or the z transform table, sorry. So 1 over s, its equivalent z is actually 1 over 1 minus z minus 1. Alright, we can also write it as z over z plus 1. Alright, you can own self proof lah. Alright, I've gone through it before. But anyway, I'll just write it as z over z plus 1. Okay, so 1 over s over here, I can write it as z over z plus 1. But if you don't understand, just proof lah, since I have a little bit time. Actually not lah. Anyway, so this is 1 over z. I can rearrange by multiplying z over z. This is equals to 1. Alright, so I'm rearranging this part into here, and I rearrange again by multiplying z over z, which is equals to 1. I'll have z times 1 is actually equals to z minus z times 1 over z is equals to 1. Ta-da! So in fact, it's different from this one. I actually remember wrongly. Lucky I go and prove to you now. Alright, so it's actually z over z minus 1. Okay, which is, where am I? That's now the table. Alright, this is wrong. It's z over z minus 1. Okay, sorry, my fault. Alright, so your 1 over s, I can simply rewrite as z over z minus 1 minus 1 over s plus a, which is also in the table. Alright, can rewrite as this form. Okay, so I will have z over z minus e minus at. Okay, so I'll just simply rewrite over here. Okay, it's the same thing. You can try this on my method, you can get this thing. Okay, and then so you have fully z transform finished. Alright, so therefore this z will be gone, because this is just to indicate that you are gonna z transform this portion, like a Laplace transform this portion. Normally you'll do that also lah, but this is our sorry, z transform. Alright, so this thing over here multiply by 1 minus z minus 1. Okay, which is also, you can rewrite as 1 minus 1 over z. If you multiply everything by z over z, alright, is it? No. Yeah, z, yeah, you can rewrite 1 as z over z, so you have z minus 1 over z. Okay, because this thing over here, if you want to apply it out together, you have z minus 1 over z. Alright, so I can simply replace my 1 minus z minus negative 1 to this form. Okay, next I'll just simply multiply it into here and here. Okay, so I have z minus 1 over z multiplied by z over z minus 1. Okay, and then minus this thing over here, gonna multiply with this now, so I have z minus 1 over z multiplied by z over z minus e minus at. Okay, and from here you can clearly see that they can actually cancel each other, so therefore this one is equals to 1 minus z minus 1 times z. You have, sorry, this z can cancel with this z, sorry, my fault. Z minus 1, so these elements will continue, while this one over here is z minus e minus at. Okay, don't feel boring, because later on you get to see this thing is actually familiar to something. Okay, so over here now what we can do is actually to rewrite this as z minus e minus at over z minus e over minus at. This thing over is equals to 1 because if you divide them each other you have equals to 1. Then minus z minus 1. Alright, I'll have this denominator, and then next what I can do is this z minus z is equals to 0 minus e minus at. I'll just write it at the back first. Alright, minus 1, I'll have 1 over here plus 1, right, divided by z minus e minus at. Okay, so I'll just simply remove the 0 and the plus sign. I move it over here. Bam! Do you find this familiar? This thing is the same answer. It's actually in your l9v8 video. Alright, if I were to paste this picture, alright, into here, if I were to crop it out, okay, alright, and then I simply shift this thing upwards to maybe hold on a while. Okay, now can you see they're actually the same? Alright, so when you zeroth order hold your transfer function, which all the way comes up to these definitions, alright, what you're doing is actually putting in a delay 1 over s. Okay, so if you were to take a look in this thing, this video from l9v8, alright, I suggest you watch this video. Alright, this is actually what? Apply the pole zero match on the LPF low pass filter with a delay. Okay, so clearly our transfer function over here is a low pass filter. We started off with a low pass filter, and then because we want to zeroth order hold it, we actually introduce a delay. You see? So therefore, if you were to compare, or if you want to design using a zeroth order hold, alright, normally you require a delay. You require one delay. Alright, and therefore this is coming from what we have just do, which is this one. And this delay is often used is because it allows you to compute your zeroth order hold. You see? Your zeroth order hold is still need to hold. So therefore this delay actually help you to actually construct your signal better. Alright, so this is another form of way, but in a way that it introduces one delay. Alright, but over here is you purposely introduce one delay. You see? And therefore I'll leave you to this thing. Alright, because we are coming to the end of this section. And the next video I'll go through the first order hold a little bit, and then we see how it goes. See you there.